In this video, I want to define a quotient group. We're going to let G be a group and H be a normal subgroup of G. We want to consider the set that consists of all the cosets of H, and that's denoted by this G over H. So we have HA, HB, HC, etc., where this A, B, C are group elements of G. And this is known as the quotient group of G by H. And the fact that I'm using the word group means I probably need to show that this is in fact a group and it does satisfy my group axioms. So I'm claiming that this G over H, which is usually read as G mod H, with coset multiplication, which I defined in a previous video, is in fact a group. In order to show it's a group, I need to show three things. First, I need to show associativity. So let's consider HA times parentheses HBHC. This is HA times HBC by definition of this coset multiplication. This is HA parentheses BC, once again, definition of coset multiplication. A, B, and C are just group elements, and we know groups are associative, so I know I can switch parentheses around there. Well, that's the same thing as HAB times HC, which is the same thing as HA times HB in parentheses times HC. So I have shown my associativity. We also need an identity element. The identity element is just the normal subgroup, or H times the identity. And this is because if I have some coset HA times the coset HE, that's the same thing as HAE, which is the same thing as HA, which is exactly what we need for the identity. Finally, we need the idea of an inverse. The inverse of the coset HA is going to be HA inverse. And this is because if I do HA inverse, definition of coset multiplication says HA inverse A, which is HE, which we just claimed to be the identity. So yes, this is a group. The next thing I want to say is G mod H is actually a homomorphic image of G. And this is a huge leap forward because it actually constructs all of the homomorphic images of any group. So as a reminder, a homomorphic image means I need a surjective homomorphism from G to G mod H. The most obvious function here to go from G to G mod H would be f of x equal to hx, its particular coset. So I need to show that this is a homomorphism. So f of xy, this would be h of, or hxy. The definition of coset says this is hxhy, which is fx, f of x, f of y. So it is a homomorphism. It also needs to be surjective, but that's pretty clear. Every single coset, so every element of GH is of the form HX. So we'll just put f of x equal to hx. So that does show it's surjective. So there is a surjective homomorphism from G to G mod H, so it is a homomorphic image. I need two more properties. The first, let's let G be a group and H a subgroup. We have that two cosets are equal, HB is equal to HB, if and only if AB inverse is in H. Well, if HA is equal to HB, then we know A belongs to HB since the identity is an element in H, so we would need EA to be in HB. So this tells me that A is equal to little hb for some little h in capital H. Multiplying both sides by B inverse gives me that AB inverse is equal to H, and remember this little h is in capital H. So if these two cosets are equal, then AB inverse must belong to H. This is an if and only if, so we need to go the other way as well. Let's suppose AB inverse belongs to H. Well, then we can write AB inverse as some element little h, where once again, little h belongs to capital H. Multiplying both sides by B, I would get A is equal to HB. So I know that A is equal to an element in H times B, so that tells me A belongs to the coset HB. And I've already proven in a previous video that if A is in the coset HB, then the coset HA is equal to the coset HB. So now I have this property. The next result follows immediately. HA is equal to H if and only if A is in H. And this follows because H can also be written as the coset HE. And now the previous thing that I just proved gives me that this would be if and only if AE inverse, which is equal to A, belongs to H, which is exactly what I need.